So our speaker today is Grace Cummings from Fermilab, who will discuss the recent search for heavy charged particles by CMS, as well as future particle collider R&D work.
Yeah, thank you guys for having me. I kind of have a little bit of a pithy title, but don't read into it too much. So I like to start this type of talk of just reminding people, what do we do as particle physicists? This is the Nuclear Particle Astro Seminar. So I know that that's not really a big deal, but the fundamental question that we always ask is, what is matter? And I know that oftentimes, particularly when you're in a nuclear group, they call things like the LHC a sledgehammer. So I like to use the sledgehammer image. And then the second question that we ask is, how does it interact? And so we've been asking and answering this question to varying degrees for a really long time now. When we started doing this, we had a very different type of detector than what we currently have today. So these imaging detectors, as I'll call them, bubble chambers, cloud chambers, nuclear emulsions, they really gave us an unprecedented clarity when it came to the interactions that we were trying to measure. So these either captured cosmic rays or they were put on the ends of beamlines, but here you were able to capture every single aspect of the event. The whole thing was taken into an image, and that let you do a couple different things. So of course, you see tracks in all of these pictures. So when you combine it with a magnetic field, you can fit that track and actually extract out your momentum. Depending on the way that the track bends, you can extract things like charge. You can do things like PID when you can see its relationship to the other things in your object, but you're also able to do a calorimetric measurement with this style of detector. Since all of these tracks are formed by ionization, which is of course how they're formed in any other tracker that you currently have today, but the thickness of the track is actually proportional to the ionization energy loss of that particle moving through. So this really gave us an unprecedented image, and that's what let us first be able to begin to understand the fundamental nature of matter. Now, of course, as we went up in energy, those types of experiments, those types of detectors no longer worked for us. You could not build a bubble chamber large enough to stop a jet that comes from anything interesting. So the detectors now look completely different. We have to have dedicated subsystems that target those things that you used to be able to get in one single image. We have trackers. You have specifically for those trajectories that you can then extract momenta, and then you have dedicated calorimeters to stop the particle. That then lets you do something like PID, as muons will actually go all the way through these detectors. So you have these different dedicated subsystems, and now the scale is wildly different. The number of channels, you don't just have one picture that you let 3 women sit down and trace tracks on. Now you have many channels of data that you have to read out. So this was really a dramatic change and how we ended up reconstructing and understanding particles at colliders. You were still able to get images out of these detectors, but you can see that now they look very different. The information is compartmentalized and it's actually reduced in its individual resolution, but it didn't impact the physics that you can actually do with these types of detectors. So I specifically showed UA1, and this here is a event display from UA1. UA1 was one of the experiments on the super proton-antiproton synchrotron at CERN. This was, of course, where they discovered the Z boson. This is a Z candidate image from UA1. This was one of their event displays, and they discovered the W boson at UA1. So you can see their calorimeter hits in their nice tracks. And then, of course, the CDF experiment, and along with the D0 experiment at the Tevatron at Fermilab, another PP bar collider, that there they discovered the top quark. And this here is a single top event in CDF. So you still have these images, but now the calorimeter systems are towers. You have the tracks that are, of course, extrapolations from radial layers of detector. When you go up, though, in this scale, in this energy, in this complexity, you can't save all of the information. So you end up having to make choices about what things you actually end up reading out. That information is reduced and compartmentalized in order to make it something that can actually fit within the bandwidth that we actually want and actually need in order to be able to run an experiment of this size. All in all, though, we've still been able, of course, to fill out the standard model. This is something that we always like to show and claim as a huge success of our field. I like to show this picture because it's completely useless if you actually want to learn anything about the standard model from it, but it gives you the hint that it's complete. It is something that is, done, standard, dusted. Why are we still building colliders? Well, of course, this doesn't even begin to address some of the limitations that we know exist within the standard model itself. We have the cosmological observation of dark matter, which isn't captured here. We know that neutrinos have mass, which of course can't be easily explained by the standard model. Then you have more what I would call theoretical considerations of why does the Higgs have the mass it does, which is addressed by hierarchy, so on and so forth. We're all measuring gravity at this moment. This beautiful, perfect circle does not show that. So the question that we're going to explore today during my seminar is, are we leaving information on the table with these large, layered, complex detectors that could actually be hiding the new physics that we're trying to understand? So this is where we're going to go from here. And I'm going to talk about an analysis in CMS that tries to address both of these problems here. So how we're actually going to do it, I know that Yale is not a CMS institute. I am, of course, on the Compact Muon Solenoid experiment, if you caught the corner of my title and if you looked at the picture that I ended up showing. So I'm going to introduce CMS a little bit to kind of put into context, what assumptions do we make in CMS and how did we ended up reducing that information for what we're actually going to study and look for. Then I'm going to talk about a search for heavy stable charged particles. This is where we start addressing, dark matter and maybe the hierarchy problem a little bit. This uses some of that low-level detector information that we normally throw away. And I'll talk about some caveats there. And then I'll talk about the future of using low-level detector information as we move to the colliders of tomorrow. We rarely have things get less complicated. So we'll see how do we actually address that challenge as we move forward. So now I'm going to talk about the machines that make collider physics specifically possible today. So the CMS experiment is one of the two general purpose experiments at the LHC. This means that it was designed to kind of see everything that you could possibly see. The LHC is, of course, a 27-kilometer ring that crosses the Franco-Swiss border right outside of Geneva, Switzerland. And I like to put a couple pictures here to kind of give you I would say, a non-traditional view of what CMS actually looks like. We're the ones that are far away from CERN's main site. So CERN's main site is over here near Atlas. CMS is about a 20-minute car ride away. If you don't have a car, you have to take the bus that goes into Geneva proper and pulls you all the way out. If you then walk from the CECI site, you end up getting off the bus, and this is what you see. This is how CMS looks like from across the field that you have to walk. Of course, what you actually see is the beautiful Mont Blanc and the Alps behind it, but my phone camera did not take that good of a picture. So unfortunately, you don't get to see that part. And then here's a picture of CMS that I took actually during LS2. So this was a couple of years ago when we were working on CMS. To give you kind of a sense of scale, I mean, people always show the pictures with the little people in it, but this is a passerelle. So this is scaffolding in the middle of CMS. This is meant for one person. So one person kind of walks across it about the size. You could think maybe about 2.5 to 3 of me radius. Okay, maybe 3.5 of me. I think I might overestimate my size radius to kind of fit in the middle there. So that's CMS in a nutshell. We're a particle flow detector. So we have these different layers that of course have the different dedicated uses, and I'm going to walk through all of them. But what you should think about with how we use this in CMS is we from the very beginning know that our measurements will always be better if you combine information from the different subsystems. If you use the tracker to inform how you actually understand your calorimeter, that lets us have a better understanding of what we're actually ending up measuring. So that's the style that was designed from the very beginning into how we actually end up using the CMS or the Compact Muon Solenoid experiment. So starting closest to the beamline, we have an all-silicon tracker in CMS. This is how we get the trajectories of our charged particles. Closest to the beamline, we have a silicon pixel tracker. This is what lets us have the finest position resolution that we can get. This lets us look for things like secondary vertices from B decays. Outside of that, we have our silicon strip tracker. Occupancy is lower. You don't need the oomph of the pixels, but we have our silicon all the way out. Immediately following our silicon tracker, we have a crystal lead tungstate calorimeter. This is mainly for electrons and photons. Of course, particles don't care that it's in the ecal, but we call this our ecal in hopes that most of our electrons and photons will deposit most of their energy here. And I will talk a little bit more about the future of crystal calorimeters in the second half of my talk. But otherwise, ecal doesn't matter so much for the analysis that I'm going to be presenting. Following ecal, we have our Hadron Calorimeter, or our HCal. It actually has a couple different sensing technologies, but this is the first time neutral hadrons can be seen in CMS. The ecal lets you see photons. This is now where neutral hadrons come in, and this is what lets CMS be hermetic and actually do missing energy measurements, since it can actually see everything. In the central region, it's a brass and scintillating plastic sampling calorimeter. In the really far forward, it's a Cherenkov detector, so it kind of depends on exactly what you're looking at. This is, I would say, my favorite subdetector of CMS, because this is what I did my PhD on. But again, doesn't really matter for the talk today. Outside of that, we have our namesake solenoid. It's the largest 3.8 Tesla magnet ever built. You could park a truck inside the bore of our magnet. This is why I was talking to you about magnets earlier today. I'm like, how big's your magnet? Well, this is how big ours is. And then immediately following that, we have our gas chambers for our muon system. This is a second layer of tracking. By this point, only muons should really be living. So that's how these things can start to combine together to give you a full picture of the event and let us actually identify all the particles. Now, the LHC collides protons at 40 megahertz. So this is every 25 nanoseconds. We actually have a new event in CMS. We can't, of course, write all of the CMS detector readout at this rate to tape. So we have a 2-level trigger system. The level 1 trigger is our hardware level trigger that says, there is something interesting here. That goes, and then eventually that'll get reduced down to a few kilohertz after a software offline trigger. So this is really important to how how you actually do an analysis in CMS, and I'll briefly mention the role of trigger. And then, of course, you need something that actually makes all of this possible to be read out, to actually be digitized and understood. And that's where the electronics come in. So this is where I spend most of my career, and most of my time has been in the electronics world. This is where you start having to make the choice of what do you save, right? You can have 6 million channels if you wanted, but what is the precision in which you read out every one of those channels? That's ultimately determined by the electronics that you actually use. So this is something that you have to keep in mind when you're designing a detector, is not only does your active material matter, but how you eventually decide to use that information and convert it into something digital that you save is really where the reduction starts to play in. So now I'm going to talk about my search for heavy stable charged particles in the tracker. So the most recent time I gave this, or when I started giving this as a seminar and not as a colloquium, I actually did it on Halloween at CERN, or excuse me, at Fermilab. This is the only Halloween joke I left in the talk, because now we're far enough away, so it stops being funny. This is people actually searching in tunnels of CERN's main campus. This is in the gas exchange tunnels. This is from a unlicensed zombie movie that was filmed in the CERN tunnels called Decay. You can find this on YouTube. I don't necessarily recommend it, but it's a really convenient picture of people searching. So that's why it stayed in the talk. So now I want to spend a little bit of time discussing the tracker because it's really an enabling technology for the search for heavy stable charged particles in CMS. So unlike the imaging detectors that I first introduced, like the bubble chambers, the way that the trackers work at the LHC is that you have these radial layers, in CMS's case of silicon, going all the way out. You have particles go through, that hits the different layers, and ultimately what it becomes is an elaborate game of connect the dots, and that's actually how you perform, you get your track, you get your fit. For the most part, this is what people need in CMS, but there's actually a lot more that goes into making the dot, let alone the whole track. So we're going to walk through it a little bit. So this is a picture of a phase 1 silicon strip layer in CMS. We're in the process of replacing all of these, but this is what's taking data right now in the heavy ion run. And so say you have a charged particle go through. This is a transverse view. You can view the gray here. I hit your screen, I apologize. You can view the gray here as your bulk silicon, and then the dark gray here as the transverse view of the strips going into the page. So you have your charged particle go through. That's of course going to ionize the silicon. In CMS, of course, anywhere that has a silicon tracker, you have an electric field from the bias across your silicon device, but you also have that 3.8 Tesla magnetic field, and these things are kind of at a funny angle, so then they drift and actually cross a couple different strips. That charge is then collected across the strips, and then from that information, and because it's shared, you can actually get a little bit better understanding of where that hit actually took place in this strip module, in CMS or in Atlas's strip modules as well. For most of us, this is all people want. You bang it there, say it's there, you do the track fitting, call it done. That's how you end up getting your thing. But there's more information encoded there. In CMS, we actually read out the charge itself, how much was actually deposited on each one of these strips. So you can back that information out, and you no longer just can interpret it as a hit. You now have something that's a proxy actually to the ionization energy loss through that piece of silicon in and of itself. So now you can actually use the DEDX, or the actual energy deposition, in the silicon tracker in addition. So this now gives you another handle to look for new physics. You're now using the tracker not just as a tracker, you can also use it as a calorimeter. And this gives us an interesting lever. So we're the Compact Muon Solenoid experiment, so I'm going to use a muon as our example. that thing flies through. This is just the beta block equation. I took this directly from the particle data group, so anyone can go and look this up. It's mostly dominated, the ionization energy loss of a charged particle moving through your material is it's sensitive to mass, but it's mostly dominated just by how fast it's moving. So this beta gamma factor. Most of the stuff at the LHC is kind of in this range. So you're kind of on this slow logarithmic rise. So most things that are standard model moving through the silicon tracker or any part of CMS, but specifically the silicon tracker and CMS will kind of have some characteristic amount of energy deposition for path length. But if you had something BSM, so think something really heavy, order TeV, hundreds of GeV, that's also charged, that's no longer going to be moving that fast in CMS. It's going to be moving a little bit slower as it goes through. That then bumps you out of this sort of minimum ionizing regime into this highly ionizing regime. So this would be a really clear and distinct signature of new physics in CMS. So this is now a handle that we can actually use to look for new physics. And it turns out that it is actually, not only is it easy to see, it's also fairly well motivated. So here I have a couple different examples of some BSM models that lets you actually get heavy stable charged particles out. The most classic, of course, is SUSY. This is something that'll address the hierarchy problem. You can get HSCPs from bound states of SUSY particles in something called our hadrons. You can have the STAUs be heavily charged, but you can also get them out of kind of more bread and butter type of things. If you just have an additional C prime going to some new exotic heavy lepton, this other type of thing would be charged, stable, heavy, and moving through CMS. So this is kind of a generically good thing to look at. And so it's kind of generically sensitive to a lot of the open questions that we have in the universe. Now, what makes this challenging is it's great that the CMS tracker can see it, but CMS has to actually write out this data. We don't have access to the the DEDX at level 1, so you have to use something else for our trigger as a proxy to actually make sure that we write out this data. Well, at the energies where we run, muons are also heavy, stable, charged particles in CMS. So a convenient thing to use is actually the muon trigger. So what this does is assuming that your HSCP will hit the muon system, which is an assumption, and this is where your model dependence starts to kick in. One, it has to hit the muon system. The other thing is CMS has to reconstruct it as a muon. So here I have our trigger efficiency plot. So this is just using signal Monte Carlo. So there's no data here. So that's actually how we have the gen beta. So how fast we actually know the thing is moving. And this is just our trigger efficiency. And you can see that we have a pretty sharp cutoff at about half beta, or about somewhere on half the speed of light. So this is where, and this then of course transitions into mass. If it's moving much slower, or if it's much heavier, it'll be moving slower. And unfortunately, we won't reconstruct this muon. So this is where our mass reach kind of stops for a muon triggered analysis in CMS. You think things that give you somewhere around a half beta. But that's of course not all you get. We wanted to talk about ionization, so now let's look at ionization. So in CMS, we use something called IH as our DEDX estimator. It's mathematically written out here. J are the different layers of the tracker in CMS. The DEDX, of course, comes from that calibrated measurement from each individual layer. You can think of it kind of as an average DEDX per layer, something like this. But here I have a plot where I have the momentum of the particle along the x-axis, and then that IH, that ionization variable, along the y-axis, and you'll notice a couple things. So first off, the gray is just QCD data. So this is just some moderate trigger min bias data that you have in CMS. You can see that that is very well concentrated in this one corner. That's good. Now you can start to see how we're going to start to design this analysis. All the colored bands here are signal Monte Carlo. So these are different kind of signal samples. So you'll notice, of course, they all have this higher ionization, which they should. That was what I pitched will actually work for you. But you'll also notice that it's banded. So you have this red band, this yellow band, and this blue band here. What separates these different color bands is actually the mass of the particle. So even though ionization isn't, super directly correlated with mass, it is mass dependent. So what you can read from this is okay, ionization gives us one, separation from standard model. That's what we want. The second thing it does is it actually gives us sensitivity to the mass of the particle that goes through. So now this transitions into a classic bump hunt in CMS. So the question would be, okay, how do you actually get IH and extract out a mass? So I said that this is about an average DEDX per layer. So set it equal to the beta block equation. This is what you get from the PDG, but you can really dig in and you can actually find the mass of your particle hidden in the side of the Tmax. What do you do when you have something kind of hidden somewhere and you're trying to get correlations? Well, what do we do as physicists? Well, we Taylor expand it and then you set everything into just some constant that you could end up measuring, and that's exactly what we do. So we end up setting this IH equal to this K, M squared over P squared plus C. K and C then are things that we experimentally measure in both Data and Monte Carlo. And then you can imagine solving this for M. So this is then how we extract the mass and actually turn this analysis into just a very classic bump hunt over smoothly falling background. So there's a couple more things you need to do before you can even look directly at the mass spectrum. So we need to actually understand what is our background in the signal region, like what does the mass spectrum even look like? So we get that normalization from what we would call an ABCD method. So this is not, since the search is using non-standard quantities, and since a lot of the backgrounds can actually come from machine problems and this sort of thing, you want to use a data-driven method. So we do that here. So you have a 2D plane, and the idea of an ABCD method is you pick two variables that are uncorrelated in background, but correlated in your signal. So you can have a signal-enriched region. In this case, we use transverse momentum, which is of course what we measure in CMS, and then we have G-strip. G-strip here is a DE/DX discriminator. I didn't talk about it too much, but if we have some questions, we can go through it. And then you have D is of course our signal region, A, B, and C are control regions. You can just take the ratio, assuming that the background between A, the background ratio between A and B is the same as C over D, and you can just solve for a background normalization. So that's what we do to get the background normalization. But we say it's a bump hunt, so we actually need a mass distribution. So the way that we do it is we invert that equation that I showed you previously and solve for M. That's kind of the easy part. Then we take the momentum distribution in the C region. So of course this has the same momentum range in PT as our signal region. And then we take the IH distribution in the B region, which will have the same ionization behavior, more or less, we hope, as our signal region overall. And we actually use that to build our ionization mass template in our signal region. And so we do just that. So this is exactly what we ended up with in our search in CMS. Here we have the mass that's extracted from that equation along our x-axis, events along the y. Data is the black dots, and our background estimation that came from these two ABCD methods that I told you about are the red, and then the yellow is the uncertainty on our background estimation. So, and then we have a couple different signal hypotheses overlaid. Despite the rather suggestive green line that you have here, unfortunately, we did not have any significant signal of new physics. So what do you do when you didn't observe new physics? Well, then of course you set a limit. And that's exactly what we did. So we have two distinct types of models that we look for. One of them are the R-hadrons. We call these hadron-like. You can see that our limit is kind of flat here. So this is this mass is a little differently defined. This is now the mass of the signal particle itself. And then this would be the cross-section above which the limit is the cross-section that if it was produced above this limit, we would be able to actually say something about it. Below this limit, we can't actually say anything about it because it's our background estimation isn't good enough. And you can see that we're kind of flat, and this is actually entirely because of the trigger. We're not really statistics limited here, we're actually systematics limited. We're just not as sensitive to these R-hadron type models. This is because a lot of them don't stay charged to actually hit our muon system. So they're not good muons. What can you do? Pick a different trigger, and we'll talk about that in a second. But here we have our STAL model, and you can see that we're doing a little bit better here. These are, of course, the ones that do look like muons. CMS, that is our namesake particle. So we're pretty confident in this one. We're able to do this pretty well. And we actually had the most strict limits at the time that this analysis came out. Atlas has recently beat us and won, but what can you do? The Atlas follow-up was actually really interesting, though. They beat us when they did the redo, but this analysis was pretty interesting because it came out following an excess in the Atlas experiment. So they did a similar result. They also have access to DE/DX in their pixel system. It's a little bit different than we do it here in CMS. And you can actually see their plot, you interpret this very similarly, except their background is this blue line instead of red in our case. And you can very clearly see that they have these 7 extra events. And this ended up being about a 3.3 sigma excess. We, of course, looked in the same region, and unfortunately, we didn't see it. But what was interesting about the Atlas excess is they were able to incorporate muon system information, and theirs actually didn't appear to be moving slowly. They matched to muons. So what's the way that you can have high ionization and something going fast? Well, the solution is to actually have something be multiply charged. So the best fit to an Atlas excess was actually a Z prime that went to a doubly charged tau prime model. That fit came out of theory while we were still doing ours in CMS because we're much slower. So that let us then actually look directly for it and set limits directly on this doubly charged tau model. And here you can see a 2D plane of the limit space where you have your doubly charged tau prime and then your Z prime model here. And the hatched region is all of what CMS was able to exclude. So we were able to look at it in a dedicated way. And we also excluded the best fit to the Atlas excess. So I think the word's still out on what it was. It seemed like maybe it was muons that had been calibrated a little bit funny, but the run 3 analyses will really tell. So we're really excited. It's still worth looking for. So the future of DEDX and CMS. So the current analysis lays the groundwork for tracker-only HSCP searches. So this is just using DEDX in the tracker. This is the first time we introduced some new models. The next search is that we're going to use a different data acquisition path. So I said the R hadrons were limited by our trigger. Instead of using a muon trigger in CMS, we're actually switching to a MET trigger. This is what Atlas does from the beginning, actually. They always use a MET trigger. That makes them a little bit more sensitive to R hadrons. I think they're now also using their muon trigger in order to do the lepton. So we have a nice healthy exchange between the two. We're also expanding our DEDX reconstruction in our tracker. So this is, a diagrammatic view of the CMS tracker. The results that I just showed you only use our central region. So what we're doing for the next version of this analysis is actually opening it up completely and using the entire space of the tracker. Ionization is not the only way you can do this. If it's truly heavy, stable, and charged, it'll be moving slowly, and you can also use the time of flight in the muon system. So this is something that we're also working on incorporating into CMS. Moving into the high luminosity LHC, things get actually a little bit stickier. So most of the IH measurement that I've showed you up until now is really dominated by the scripts, or what we call in CMS our outer tracker. Our outer tracker is being replaced, and we actually will no longer save DEDX information. So HLHC will not be able to use DEDX in the CMS outer tracker. We will only have it in pixels. So that's going to dramatically change how we do it. But we now have a little bit other phase space that we're entering. So I work on the CMS high granularity calorimeter upgrade. So this is where we're replacing our entire NCAP system with a combination of silicon and scintillating plastic calorimeter, and most of it's silicon. So now we end up having much, much, much farther forward, very, very, very granular silicon. So this will be something that might not touch on the traditional HSCP models that I've talked about today, but opens up new space for things like monopoles. So this is something that I'm personally really excited about. And then we also will extend our pixel, which will have DEDX up to an 804. So it stops at 2.5 right now. So this is a huge space. Yeah.
Before you get too much further into the future, I'm still trying to understand exactly. So the DEDX information was being stored at the 20 megahertz or 40 megahertz rate, but then you wasn't being used for any analysis until you used it. So that's the missing information that you did.
It's you don't have access to it at the 40 megahertz. It's only available after the HLT fires. So it's something that the tracker does buffer, but it's only ever saved if it has a high level trigger decision. So it's only saved at the 1 to 2 kilohertz rate.
Which is like that's the decision about if it sees a muon track, then it decides to save it.
Okay. Exactly. Or a metric.
And nobody had looked at the DEDX.
Other people had done this before. So this is just the run 2 version of this. There is also a run 1 of the LHC search of this. I use it as an example of that. It's something that not everyone saves, and CMS just happened to. So like in Atlas, for example, their DEDX search only uses pixel. Atlas does have strip silicon. Atlas people in here, please tell me. They do have strip silicon. I don't believe DEDX is saved in their strip silicon. So they only have it in their pixel. In CMS, we have it in the pixel and we have it in the strip. But moving to HLLHC, we actually will not have it in the strip either.
So part of
we kind of had it as an accident. They didn't design for it.
Part of the argument is like the whole goal, you get bigger detectors, you're trying to figure out what the minimum amount of information you need to save is.
Yeah.
And they're trying to get rid of this DX information. Yeah. And you're showing that there's kind of
there is
important analysis you can do with it that you can do without it.
Yeah, precisely.
Sorry, I was a bit slow following.
No. It's a great question. Now, people who I like to think there's two ways people approach searches at the LHC. There's people who are like, man, I have this cool signature, let's use it to look for new physics. And there's people who are like, I am really mad that there's dark matter. I have a dark matter model. Let me look for dark matter. These are often end up being the same, but they're not actually the same people. The philosophies are very different. So if you truly believe that our hadrons are where new physics is and it's Susie, if those things are heavy, it would also come up in muon time of flight. CMS is also, I haven't have it mentioned here because it doesn't fit the narrative, but CMS is adding a barrel timing layer, which will do precision timing right outside of the tracker. That would probably, it's probably going to murder DEDX limits on itself just because its sensitivity will be so much higher. But that only would tell you things that are slow. It wouldn't touch things that are multiply charged. So it kind of, you lose generality when you go this way. I was actually just having this conversation yesterday, 2 days ago, when we were talking about future collider stuff, and we're deciding readout and this kind of thing. And I'm like, I've never had someone come up to, maybe it's just that I'm in BSM land, which is also very different than standard model measurement land at the LHC. But I've never had someone come up and be like, man, I wish I had one more digit of precision. People always come up and they're like, man, I wish I had one whole layer of detector read out that wasn't there before. So this is kind of where you can probably guess which camp I lean a little bit more into. But so it goes. Any more questions on this? Or we can also do them at the end. But if not, I'm gonna move on a little bit. So that was actually a perfect transition to talking about future colliders. So now I'm going to talk about low-level information that we can do there. And I actually like to start it with this. So maybe I'm a bit, I don't want to say cynical, but sometimes when you talk about the future of the field, it feels a little bit like fortune telling, right? Like we want to say, this is what we want to do, but then of course things actually come in and make it and end up having it be different. This is actually a placard from a business that's near my house. This is a metaphysical shop that is on North Avenue. And I like it because it has crystals as part of the future. And I told you I was going to talk about lead tungstate crystals of the future, but it comes with a caveat that this metaphysical shop is now closed. So take it for whatever it's worth. But this is where we are. So at the LHC, right, the way that we actually study the heaviest particles that we have is that we collide particles that are not fundamental and then measure whatever comes out. That gives us a really complicated event space. We have really busy events that have this large amount of QCD background that bleeds into everything else. That's why when people are thinking about what do we want to do next, there is a large push to have E plus, E minus, or electron-positron colliders. And it's for a couple of different reasons. One, you have a good control over the center of mass energy. I use, missing transverse momentum is what I talked about here. You could actually just do missing energy from the start. It doesn't just have to be in the transverse plane because you have that really good control. You also have cleaner jet physics. So when you have, a Higgs boson that decays hadronically, there's only so good you can get because actually the jet resolution is limited by all of the backgrounds that we have in the detector. Here, you won't have that hadronic background, so it actually lets you do a lot cleaner style of jet physics. So this is why this type of machine is where people are thinking to go. It's something that we don't really have access to at the HLHC. So it's a good thing that we just concluded just a couple of years ago at this point, we concluded, the P5 process, and what came out of it for collider physics is the next highest thing that they wanted to do was an offshore Higgs factory. And of course, when they say Higgs factory, they mean an E plus, E minus collider. And there's a couple different options. Here I have the FCC. You have, of course, ILC, which of course has the best PR with Hello Kitty riding a cryostat. So it goes. The Higgs factory portion is, of course, only one line. So here on this plot, I have center of mass energy of your E plus, E minus collider, and then I have the luminosity. This, of course, determines what physics you can actually do. How many, how many E plus, E minus collisions do you have at any given time? Each one of these lines represents a different possible E plus, E minus collider configuration. The Higgs factory part that P5 recommended is just somewhere in this pink box, somewhere between 240 and 250 GeV of center of mass energy. This is just what maximizes the Higgs-Strelung production mechanism where you have a Z radiate off a Higgs and another Z, or just a Higgs and a Z. You can also do it kind of at 230, but that's kind of splitting hairs at this point. Now, of course, you don't just buy one point, you end up buying the whole line. And which line you buy actually introduces new physics cases. So I'm going to talk a little bit about this, these steeply falling lines here, which are the circular E plus E minus Higgs factories. So you can think things like FCCEE, Future Circular Collider at CERN, or you can think of things like the CEPC, which was the Chinese version, which was very similar. Here, up in this upper region, these lower center of mass energies, the physics program actually shifts a little bit. So this is running at what we would call the Z pole, so just making oodles and caboodles of Z's. In this case, we call it tera Z in FCC speak. And what this then becomes, besides just a precision electroweak machine, is you also have a flavor physics factory. So this is now something similar to what I would consider LHCb or Bell 2 style physics program. So this now introduces new physics goals that have to go along, of course, with the Higgs measurement. When you have new physics goals, of course, this then means that you now have different detector constraints. So if you want to do precision B physics, something that's really important to precision B physics that's not relevant to the Higgs program is you actually want 2% over square root of V electromagnetic energy resolution. This is really state-of-the-art, pushing it style electromagnetic energy resolution. That's how you can actually get some rare, probe some flavor stuff. I'm not a flavor physicist, I'm sorry. I should say more about it. But that's really where you can start to get into the meat of this. The most stringent Higgs calorimeter, I'm going to qualify with the Higgs calorimeter design goal, is actually this 3 to 4% jet energy resolution at about 100 GeV. This is for Higgs physics. This would let you tell apart hadronic W's and Z's. This is not something that we can currently do at the LHC. So this is something that you would want to have access to at a Higgs factory, so you can actually start to begin to pin down some of the branching fractions. So if you want to do that precision electromagnetic energy resolution, the only way that you can really get that really state-of-the-art measurement is to go to scintillating crystals. So the reason that you have scintillating crystals is because in this case, it's a homogeneous calorimeter. When I say homogeneous, it means the absorber material, or the thing that initiates your cascade, and your active material, the thing that produces the signal that you actually end up measuring, are the same. In electromagnetic showers, all of the energy that's deposited is ultimately visible. So ultimately will end up in soft photons and soft electrons. So this is where you can really pump up your photostatistics with a scintillating crystal and really get it all. That's how you can achieve that. So this is not necessarily a particularly hard thing to do. The hadrons are a little bit more challenging. So hadronic energy deposition is complicated because you have your hadron come in, it has a strong interaction with the nucleus of your absorber. And then it goes to secondary hadrons, right? This is a hadronic cascade. Everyone knows this. If that secondary hadron is a pi 0, that actually goes to 2 photons, and then you have an electromagnetic cascade. So this would then bump you back into that, homogeneous calorimeters would kind of work best type of regime. But not all of it goes to pi 0s. A lot of it goes to other stuff. So, charged pions, which would then have another cascade, protons. But then you start having things like neutrons. This will knock around in your detector forever. In CMS, this would just leave the detector before, outside of that 25 nanosecond window in some cases. So it's just gone, missing energy from the standpoint of the detector. You can also have more complicated things like nuclear excitations and nuclear breakups, which might not even produce any sort of visible signal. So some of this is fundamentally always going to be lost in information. And this is why hadronic energy resolution is harder, hadronic energy measurement is harder. And that manifests in then what we call this E over H ratio. So basically, how much does 1 GeV of energy deposited electromagnetically, that normally is not the same as what the visible thing that you measure of 1 GeV of hadronic energy deposited. And that's why this response is normally different between those two. This is one of the things that can degrade the resolution of your calorimeter. To add insult to injury, the fluctuations of how much goes to neutral pions and how much doesn't go to neutral pions also changes event to event. So this then adds one more way that your energy resolution can start to be bled out. There's a couple ways that you can address this. The most famous of these is, of course, compensation. So then you just kind of ignore this problem that the response is different, and you make 1 G of electromagnetic energy resolution look like 1 GeV of hadronic energy resolution. Now, the way that you do that is, unfortunately, the only way you can do that is you can't bring the hadronic energy up. You can't make more of it become visible, but you can quench down the response to electromagnetic deposition. And you can do that in sampling calorimeters. So what you would do is you interleave high Z material to quench kind of those soft photons that ultimately come out of your electromagnetic energy depositions. So you can do this, then one GeV looks the same everywhere, then your calorimeter just runs like normal. Easy peasy, great. If you can only do it with a sampling calorimeter, you then can't get that precision electromagnetic energy resolution that you actually want for the B physics at tera Z. So the next question you can ask is, what if instead of making the response the same, what if you can just measure the different components separately? And that's what I have been working on trying to do. So now take a hadronic shower in a scintillating crystal. Both of the branches of the hadronic shower will actually produce scintillation light. Great, that's what we want. We want what we're trying to measure to actually produce something visible. That's pretty good. But the electromagnetic portion will actually produce most of the Cherenkov light in your crystal. So now you have a way to actually have a proxy for the different amount of energy deposited, and this can give you an event-by-event correction for the fact that it will fluctuate. So this now gives you a handle to that uncertainty. This is something that will 100% be needed if we want to reach the calorimetry goals for the Higgs program, because CMS is currently running with a mixed calorimeter system with our crystal calorimeter followed by a brass and scintillating plastic sampling calorimeter behind. And you can see here that the early showering events, so things that come in our electromagnetic calorimeter, the response just tanks for CMS. And this is one of the main things that actually degrades our jet resolution in CMS. So if you want to have a crystal calorimeter at an FCC-EE style collider, you will need to do something a little bit more than what we've been doing now. Now, the challenge, of course, comes from separating the Cherenkov and the scintillation light. There's two ways you can do it. The first one is just with wavelength. Scintillation, of course, has some, distinct peak, and then the Cherenkov is just going to be some smoothly falling distribution on top of it. The second thing that you can do is time structure. So here you can think of charge is along the y-axis, and then time here. This is just the waveform that you would read out in your digitizer. The Cherenkov is inherently prompt, so it's going to be really on the rising edge of your pulse. The scintillation has a time constant, so it'll come a little bit later. You can imagine using a filter and just smacking off a bunch of it, and then everything that you would measure would be Cherenkov light. But you have to be really sure that you understand the tail of your distribution, and we all know that measuring tails can be a little bit hard. You can also think that you could loosen that requirement a little bit, accept a bunch more Cherenkov light, let the scintillation come in, and then if you could somehow just fit it directly, you could actually get both out of one measurement. And this is what we have been mainly exploring, using dominating waveform analysis to actually do the separation, combining with a filter in order to enhance the Cherenkov light. So we actually went and tried to test this. So last year, we did an electron test beam at DAISY. So we used 2 GeV electrons off of their Petro 2 beamline. We mainly focused in BGO crystals. So this is one scintillating crystal flavor. It's not the lead tungstate of CMS, but you don't necessarily need something that fast. And we had two main goals. We wanted to characterize a couple different crystals, and we wanted to see if we could do an energy measurement, or at least the best you could do with one single crystal, which is not great, but it's also not negligible. So that's what we went and did. So this is our setup. You can see that it's a variable rat's nest. The crystal, of course, lives here. The main thing I want you to take from this is that we actually had a motion stage, and I'll talk about why briefly. We had 2 amplification stages, and there are 4 SIPMs on either side. I always like to show people what the bench actually ended up looking like. This is, of course, the box that you see here. And then you can see our water cooling system and our calibration system and all this kind of stuff. It really didn't need to be water cooled. It was way over engineered. It could have been a lot simpler, but so it goes. Next time I'm going to put my foot down, I think a little bit harder when it comes to some of the other things that we put in our box. So for the motion stage, we did it in order to have angle scans. So I said that you can separate Cherenkov light with time analysis or waveform analysis, and you can also do it with wavelength. But in order to verify that you're actually extracting Cherenkov light, you can use the fact that it's really directional. So how much Cherenkov you accept would actually be really dependent on the angle of incidence into your crystal. Since it has that opening angle, you can hit it at what we would call the Cherenkov angle to actually accept the most Cherenkov light. So we do that. Basically, as you scan angles, if it's scintillation light, the response shouldn't change once you correct for path length. If it's Cherenkov light, the response definitely should change. So this is a second way that we can be sure that we're actually accepting Cherenkov light. So what did we end up seeing? So we used a lead fluoride crystal, which of course doesn't scintillate as our control. That gave us this nice green peak here. Boom, super fast, super clean, great, looks like a Cherenkov pulse. Then here we have our two different BGO waveforms that you can see. The all scintillation is unfiltered. And you can see, yeah, we have this, it's got some rising edge and then it has a bunch of stuff that's really slow. BGO is a slow scintillating crystal. Okay, fine. But then you have it filtered. And we put a really harsh filter on this. And you can see that maybe it's like ever so slightly faster. All right, so maybe that rising edge is a little bit faster. These are really similar, so this made the waveform analysis that we wanted to do a little bit more challenging. But we still think that we could do it. And so if you ever want to know about the rate of change of something or really understand our rising edge, where things should live, what do? Well, you take a derivative, right? You want to understand the rate of change of something. If it's there, this should be more sensitive to it. So we took that one photoelectron Cherenkov pulse, and we didn't do a full derivative, but instead we did a single delay line technique where we just subtracted the 2 nanosecond prior or 2 nanosecond after time slice to get this approximation of a derivative of changing. So you can see, okay, this then becomes something else peaky. Something peaky went to something peaky. Okay, fine. Great. Then how do you get the scintillation pulse? So we took this one photoelectron Cherenkov pulse and then we convoluted it with the derivative of an exponential decay, because that's what it should actually look like in a scintillating crystal. And then you get something that looks like this. Okay, that now looks a little bit different. So now we think we have two shapes that we should be able to fit and actually start to extract something. So then the next question is, how do you actually get pulse shapes into energy? So that's then the second step. So this is just the distribution of max amplitudes of individual pulses that we collected from our crystal. You can see that we have a peak, and that you should interpret as just the characteristic energy deposition of 2 GeV electrons inside a crystal of the size that we had. Then of course you have some tail here. So great, take events from the most probable value, normalize that to the energy deposited in the crystal. We just took this from Jayant. So, this is why it's not perfect. You have to then assume some systematic with Jayant, but we've been using BGO since L3, so since LEP. So we think that our understanding of it's pretty good. And then you fit the pulses that actually come from that region. So pulses from the peak, normalized to energy, and then you can say, okay, that will then let us do photoelectrons per GeV of energy deposition. And here you can actually see that working. So this is the BGO pulse. This is an average pulse that makes it a little bit clearer. The black is, of course, our real one. The red is the total fit. The blue here is that Cherenkov shape. And then the green here is the scintillation shape. So you can actually see that we are getting a mix of both of these signals. So we're pretty excited about that. So this is then the scintillation. This is then what we saw. So this is scintillation photoelectrons per GeV. And then this is the angle scan that we did. And you can see that for the most part, we're actually pretty flat. These channels were unfiltered. These were our filtered channels. So scintillation's kind of depending, like we saw, you can see that there's large uncertainties on it, but for the most part, it's flat. Then if you look at it for Cherenkov photoelectrons per GeV, you can clearly see the Cherenkov peak. So we're pretty confident that we actually were extracting out Cherenkov photons. And if you take something that is more indicative of a real way you would run a calorimeter, which would be about 90 degrees in our case, so particles going straight down your crystal. If you're optimistic and you assume that you have 4 active channels, not 2, like you can clearly see on this plot, assuming that we had all 4 of our SIPMs nice and happy and behaving well, we were getting about 160 photoelectrons per GeV. That doesn't seem like a lot, but we were super excited because this was a research program that was pursued in the past, and they abandoned it because they thought that 50 photoelectrons per GeV was what you actually needed to do this, and they never actually managed to do that. So we were comfortably exceeding our goal with one single crystal test. So we were super excited for that. So that now lets us give this peek into the future. So we want to actually do a real measurement, and the way to do a real measurement is you need to build a matrix that's actually large enough to contain a full electromagnetic shower. And that's what we've done. So we've purchased a 5x5 BGO crystal matrix for both lateral and transverse containment. And it's going to give us about 22 radiation lengths. So most of the things that we would want to see, and this is exactly the CMS EM calorimeter thickness. So now we're starting to get into some real physics range. Here you can see that it's not completely homogeneous. We actually have a more highly granular crystal layer in the front, This is actually a prototype for an FCC detector, which you can see here, which would allow us to actually do particle ID, to do actually pi zero versus photon separation or versus electron separation. So we're pretty excited about that. So that's one thing we want to do. We want to see, do we get the precision electromagnetic energy resolution we wanted? The next thing that you want to do, though, to make sure it actually works, is to do hadron energy resolution. This matrix, of course, won't capture it, but we don't want it to. So we're actually going to put a dual readout hadron calorimeter behind it, which is a sampling style calorimeter that I have some pictures of in the backup if people want to see. So we'll do a joint system test beam with them, and that will really be the ultimate test of can we actually use this to do precision calorimetry. And then, yeah, the DR crystal calorimeter is the baseline for one of the FCC detector concepts. So this is going to be hopefully incorporated into the IDEA detector as it goes. And right now, I'm actually a level 3 in the DOE Higgs Factory consortium that starts to prioritize funding for this. So they're taking dual readout very seriously. So it's good that we are too. So that brings me to my summary. Low-level decisions about detector readout directly impact your physics reach. We already talked about it a little bit. So things that, you couldn't do otherwise are sometimes hidden in the things that we decide to throw away. Whether they matter to people, though, is the question that we all then have to end up going to bat for. So I presented the heavy stable charge particle search in CMS. That was a run 2 result. We're working on our run 3 result right now, which has that extension in it. And to us, that's really important because this is the last time we'll actually be able to do it this way in CMS. Otherwise, we're going to have to adapt and see what we can do to really make sure that we can maximize our understanding of the HLHC data. And then finally, we have enabling hardware. The new accelerators that we have on the horizon are really going to provide different challenges. And especially for people like me, I'm a BSM person that, joined the field well after the Higgs discovery. This is now a totally new type of detector that I'm trying to make sure that I can actually think through with what I want to build. And dual readout crystals for precision measurements hopefully will be a part of the future. Right now, it's promising. So thank you for your attention. Yes.
I think it's me. Hi, nice talk. I have I have a few questions. So I worked on heavy ion, so I have, so I understand we don't do CMS. I have the way we analyze data or I guess interact with the proton-proton data is a little bit different, I think, than like other particle physicists. So when you say you take the run 2, have you ever thought for the beyond the standard model searches of seeing what happens if you take the different energies, or is the idea like saying if I do it at 2.7 TeV versus 5, or I guess you get up to 12, I think, with proton-proton, and seeing whether or not the statistics or the spectra changes?
So this is a really good question. And I had this conversation last week, actually. I went to UIUC and they asked me a similar question, like, why don't you do this in the heavy ion data, Grace? Like, it's a different energy, you should do it. So the lower energies, there's 2 reasons why we don't do exactly this one. I would say the main reason is that people haven't thought to do it. And everyone in proton-proton is like, I can't use heavy ion data. That's probably the real reason. But the second reason that's a little bit more well-motivated is the run 1 proton-proton analysis. So that was done at 7 and 8 TeV. So that pushed the max a lot lower. And then that one actually almost hits the end of the LEP exclusions at the 2 GeV center of mass energy range. So it's one of those things where I'd have to make sure that it isn't 100% excluded to look at the lower center of mass energies, but there's a chance that they are excluded already.
I see.
Which is why people haven't looked, because you would have to be, because the run 1 naturally pushes down these into the much lower region, and the LEP limits are actually super good up to like 300 GeV or so.
Okay.
So there, probably for certain models you would gain, but you'd have to be a little bit clever with it.
And then when you make the assumption to use the muon trigger, the idea is that if this is BSM, it has to be a stable particle, right? So it should act uh, uh, like a MIP, minimum ionizing particle. That's right, the idea, right? Behind that, I wasn't sure if I.
So they did the muon trigger for two reasons. One, if you assume that it's stable and you assume that it's charged, it's a really reasonable assumption that it'll hit the muon system in CMS.
Yeah.
Now, this is not even a very realistic model, even from a SUSY standpoint. Most SUSY models also have a decay to an LSP, which is then missing in the detector and then goes to jets or whatever. That wouldn't actually work with the muon system trigger, so you'd have to switch to a metric.
Let's see.
The lepton trigger for the first version of the analysis, just because it's simpler to use in CMS.
Mm-hmm.
The next version of the analysis will actually have both muon triggered and MET triggered analyses.
Yeah, okay. And then, sorry, I have one last one. Sorry, I can't tell. I can only see you, so if apologies if there's more questions and I'm taking over. But for the crystals, so before I did heavy ions, I worked on neutrino-less beta decay, and they use scintillating bolometers, or that was the idea. Well, they wanted to use scintillating bolometers for the next experiment, but then the problem became that the only distributor of these crystals was Russia, and then panic ensued. And then I left before they figured stuff out. So I don't know what ended up happening. But for these, I guess, just scintillating crystals, is this a concern or not really?
Oh, 100%. No, it's horrible right now. So the only other place you can buy this type of crystal is China.
Right.
And we currently, half of our matrix is stuck in export control.
Oh, really? Oh, no. Yeah.
On the Chinese side, actually. So it was
okay.
Really, so they sent them to us. Then the company was like, actually, we didn't do export control properly. Can you send them back to us? So then we sent them back to us. And we sent them back to them. And
yeah, I see.
The first, we have all but 8 of the big crystals and a lot of actually backup crystals, but we don't have any of the front part of the matrix right now.
Yeah. It's
no, you really hit it on the head. So if anyone wants to start a crystal growing company, I highly you do this. So no, you hit it. You hit it directly. Because Russia's out completely. So that leaves China.
Right. For now.
At
least. Sorry. But yeah, thank you. It was a really nice talk. So
thank you.
It's pretty cool.
Joining it on Zoom.
So if I understand correctly, your whole goal with the crystals is to separate out the electromagnetic and hadronic energy. So how exactly would you then use that when you analyze data? Like, would you use it for PID or?
So you actually use it, maybe I hope I had this backup slide. Haha, there it is. So there's actually measurements of the relationship between the scintillation and the Cherenkov that you can do as a calibration. So basically what you would do is you'd be like, this is the ratio. I actually exist here on the energy deposition, and then you can use that as an additional correction, is the way that you would end up doing. We have not gotten this far yet, but in principle, this is how you would do it.
So it's a correction on what exactly?
You use it to understand the relationship between how many photons you measured and actually how many GeV of energy, how much energy was deposited.
Okay.
So it's that conversion.
So it's a more precise measurement of energy. Okay.
Yeah, exactly. You can also, people have told me, I have not done this study, so take it for what it's worth. You can get some additional types of discrimination out of it. So I know that some people have used, so the hadronic calorimeter backend is actually the way that they do it are these dedicated like individual fibers of scintillating fibers and then Cherenkov radiators in this kind of matrix, and each one of these is about 1 centimeter. So some people have simulated this and have thrown this into things like tau reconstruction And apparently the Cherenkov and the scintillation light does actually impact things like tau reconstruction a little bit better. But that's also like a Delphus analysis, so but take it for what it's worth. I was surprised that it wasn't just the fact that this is highly granular to do like substructure of the tau. They promised me that it was actually the Cherenkov light. We'll see. So there's probably more information there, but right now we're not even sure we're getting enough light, so we haven't moved into that part yet. But once it's there, people will use it, right? And I think that that's what's exciting. It's like once you have it, then you can see people can kind of run with it. And I'm sure people will be finding new ways to use it the entire lifetime of the detector, would be my hope.
How much does one of the crystals cost?
That's a good question. So the target to make it like a production ready type of thing, they would ideally want it to be less than $2 a cubic centimeter. If you actually wanted to go and buy a crystal, I think it's a couple hundred to a couple thousand, depending on the crystal, for like one. Mm-hmm. Like I think when I write proposals, I put in like $1,500 to $2,000 a crystal when I have tried to do budgets out. You can get them a little bit cheaper, you can get them a little bit more expensive. Right now, it's really weird to get them, so I think the price is going to go up dramatically, because the first time, the crystals that we did get came through right when the first round of tariffs hit, so that cost us almost, 50% more than we were expecting. So there's a really high error bar on the crystals right now, but I would say normally about 1,000 to 2,000. You can reuse them though. This wouldn't really help. We would need so many for something like an FCC detector that you couldn't. But so at LEP, the L3 detector, which was one of the LEP detectors, had a BGO crystal calorimeter, and those crystals are still being used. If anyone has heard of the recent PADME result that came out, which is this like very specific electron resonance thing, their calorimeter is actually all made of L3 crystals. So they don't go bad as long as you don't irradiate them. Then they go super bad, as we're learning in CMS. But
the flux from being in the detector doesn't affect them?
For FCC?
Yeah.
It shouldn't. L3 it didn't. Or LEP, excuse me, it didn't. But the beam energy was also much lower, and the luminosity was much lower. I think that we'll feel it a little bit, but I don't think it should be. I mean, CMS also works, right? It's just that they get dark, a little bit darker. So I think for the electron positron machines, it shouldn't be a problem. It's really the hadronic flux that gets you. So of course they'll take damage from jets like anyone would, but there should be fewer of them.
If there are no other questions, then thank you for